Hello everyone, Gabe here from Ubisoft, and I am joined by the Master of All Knowledge once again. Hello, sir.
Hi.
How are you?
Good.
What are we doing today?
A little bit of CPU, a little bit of RAM, a little bit of fun.
Yeah, so far we've covered 3 episodes of CPU.
Yes.
Now we're going to wrap up CPU.
Yes.
And then move on into RAM because they kind of tie in with each other,
Yeah,
right?
we'll touch on RAM a little bit. This will be a nice segue into RAM, which is after this episode.
I like segues. Let's get to it.
So, let's create a little hypothetical problem. Let's say that we have a zombie.
A zombie.
There's a zombie in your video game. And we would like to have a lot of zombies in our video game because people like to do that. A lot of zombies, you can do something with them. And as you know with zombies, they walk around.
Yeah.
They slowly move. So we would like our zombie to move, right?
Okay.
We are somewhere in our code. It's looping around like we've been talking about. And during this frame, this is a frame that we are rendering and going through. We would like our zombie to go from this location here to some other location, which is represented by this beautiful, beautiful arrow. So a move like this is actually 2 moves.
Yeah.
It's a move in the X direction and a move in the Y direction.
Yes.
So we move a little bit X, a little bit Y. That means that we moved diagonally, basically. Great. It's a very slow zombie.
Yeah.
Cool. So let's then imagine, since we're going to touch a little bit on RAM, that we have these 2 values, the X value and the Y value, we have it in memory. And for the X value, we have the value 10, and for Y, we have 18. Let's just imagine this is the X and Y coordinates. And we would like to update them. We have some code that updates the X and Y value. So let's imagine that these are the memory address of those values. Just again, this is going to be a lot of hypothetical, but this should at least give you some insight of the problem here and what we're going to go into. So let's imagine that the X value is at memory address number 100. So this is in hexadecimal, but it's fine. And then the Y value is in 104. Great. So we would like to update these values. So we have some code. And we load from 100 into A. We add 1 to A, like we've been talking about, and then we store into 100 whatever is in A. So you can see that it was 10 and is now 11.
So we moved.
We moved a little bit on X.
Moved on the X.
Yeah.
So we're just shuffling.
You're shuffling.
Shuffling to the side.
The user won't notice this because we usually do all the updates first, whatever the update needs to happen, and then we take all that information and draw that. So we can do all sorts of crazy stuff. It's only the last, basically the last values we care about. It's the intermediate values like this don't matter. So, and then we do the same thing for Y. We load from 104, add 1 to it, and store. And you can see that we are reusing A, which is the register inside the CPU. And in this case, it's fine. But like we talked about before, loading from RAM takes time. So the first line, load A, takes some time. Adding together might take some time. Storing also takes some time. And
Take some time here, though. We're talking
we're talking nanoseconds or maybe microseconds, but still, they add up.
Yeah.
If you want to have 1 million zombies, you got to be efficient, right? And this is kind of the thing we're talking about today. So let's say that you have RAM, which is just basically a line of numbers. And let's say that in this section of RAM, these are just a bunch of coordinates for zombies. So from 92 to 96, that's the X and Y of one zombie. Then we have our zombie, and then some other zombie after that. So let's say we want to move all of those zombies around a little bit. Great. So we would then add another one. Here's one for 108 and 112. Again, we're reusing A. We're adding 1 to it, storing it, loading A, adding on to it, storing it. So do you see the problem here?
We're loading A lot.
We're loading into A a lot. We're doing a lot of loads. And we talked about last time, there's a way to optimize that.
Is it because is it the gaps between 100 and 104?
Yeah. Well, we could do 2 loads at the same time, right? We could load and then do the adds.
Yeah.
So let's shuffle things around a little bit. But this is a problem, right? So what is the bug here? There's a bug in this code.
Ooh.
So
my brain skills are not strong enough for this.
It's fine. So we load from 100 into A.
Yeah.
So A contains 11.
It's continuously writing over A. Isn't
Yeah.
It? Okay. Yeah.
Yeah. So A will then contain what is in
whatever's the last one.
Yeah. And then we'll add. So we are basically doing +4.
Yeah.
So that doesn't work. And
then
then
we're storing
into. Basically, we're storing into all of them.
Yeah.
So we're storing into 100, 104, 108, and 112.
The same number.
Same number. So that's going to be really buggy.
Yeah.
So that's not going to work. And of course, you don't write it like this, but I'm setting it up as a
simplified.
Simplified. So what you would do is you would use each register. Let's say you have 4 registers. You load into each one. You add increment 1, and then you store 1. Again, there's a problem here. So the loads, okay, we're never gonna get away from those, right? Or might not get away from those. We'll go more into that in the RAM. We actually can avoid a lot of these loads. But all the adds, you can see they are the same action. Like increment A by 1, increment B by 1, etc. And then the store is kind of, like we see a lot of similarities here. What if there was some sort of mechanism to simplify this?
I feel like there is a mechanism to simplify this.
Spoilers, there is. So let's change subject a little bit.
Ooh.
Yes.
Ooh, 2 different colors.
2 different colors. This is a sheet of white paper.
Okay.
And I have a task for you, Gabe.
Okay.
Are you ready?
I'm ready.
I would like you to punch a hole in this piece of paper because we want to put the paper in some sort of binder, right?
Do I smash?
So
I don't. Okay.
you put one of those
I
holes.
thought you wanted me to punch through the screen.
No, thank you.
So I don't want to do that. That screen costs money.
It's a nice screen.
Yeah.
So, I mean, it's a classic task.
Yep.
Punching a hole in a paper. You do
Though punching one hole in the middle is not very efficient.
Well,
and that paper is just gonna float around.
Maybe the box can contain it, and yeah. Maybe. So what you could use? Is there a specialized tool for this?
Yeah, there's a hole puncher.
Hole puncher. It's a pretty picture.
Yeah.
And yeah, it's a picture of a hole puncher. So yeah, you use this. You punch a hole in the paper. Job is done. Do you see any similarities here? You get the paper from wherever it was. You perform the action on the paper.
You send it back.
You send it back. So it's the load, the add, and the store. Okay, great. So again.
Yes, 2 holes.
2 holes. That's more like when I was in school.
Yeah.
So again,
I'm used to the 3.
Used to the 3.
Yeah.
Cool. So 2 hole. Is there a specialized tool for this?
Probably.
Yeah.
There you go.
That's it.
2-hole puncher.
2-hole puncher. And then you align up the paper. You
smash,
and then you have 2 holes. Cool. Next project.
Well, that's a lot of holes.
Can we do this?
I mean, you can if you have a very, very specialized tool.
Or what if we just use the first one? Like we can't use this one.
Yeah.
It's gonna kind of mess up, right? Or you probably could align it up or something. This one would probably work, right?
But it's really slow.
There we go.
Yeah.
There we go. You can solve this problem with the hole puncher. You just have to line it up, be careful, make sure that everything is lined up, and then you go.
And if you're not perfect, you're gonna compromise the integrity of that sheet of paper.
There we go. You might have a bug. A hole in the wrong place.
Yes.
So what if there is a specialized tool to do this? Oh, by the way, there is.
Oh, okay.
I was like,
why would you ever need that many holes on a piece of paper?
I don't know, but like you say here, there is a tool for this job.
I'm glad it exists.
So what if you, in like the same vein as this is, what if there was a tool where you could line up all the numbers into memory, you set up all the operations correctly, and then you just do hole punch.
Smack.
You say add, and you say add once or few times, basically. So this is a thing called, you might have heard of SIMD, you might have heard of MMX, you might have heard of SSE, and you might have heard of AVX.
I know AVX. AVX is the one I've heard.
Yeah. So these are all in the same genre of optimizations. So it's what I'm going to talk about is SIMD, but you can Google more things like this. SIMD means single instruction, multiple data. So all of those MMX, SSE versions 1 through 4 point whatever, and then AVX. AVX is more for linear algebra things. MMX is for integers, SSE is for floating point numbers.
AVX is specific to Intel CPUs though too, right?
Might be, I'm not sure. You can correct me on that one. So you could have the idea that you line up the data and then you make everything nice and tidy, and then you do hole punch, and then everything is added together. So that would be pretty nice if we have the zombie. So if you go back to this, if we have the zombie, we know that we want to load in a bunch of numbers, put them in some sort of right location. We want to do an operation on them, and then store the results. So let's imagine there's another register called X0, and we load 100 into that. But we also load the number we want to add to it. So in X1 goes 1 because we want to increment the number by 1. So we keep doing this. So this seems like a little bit more that we're doing, but in actuality, we can go into that in the RAM episode, but this is fine. We're okay in here.
And this is this just to understand, this is the CPU loading things onto RAM?
Yes,
Okay.
loading from RAM into basically small memory slots on the CPU.
Okay.
So the things we've been talking about, A, B, and C, those are registers within the CPU. They're
So
normally-
very, very close. This is what we talked about with the speed timing comparison last
Yes.
time. There was the CPU cycle, and then there was the L3 cache, I think, or one of the caches.
Yeah, so this is even closer than the caches.
Okay.
But they are, like a cache can store many numbers or up to megabytes of data. Registers can only hold like one number.
Oh, okay. Very small.
It's basically thinking of like, I put this on my desk, I can work with it, and then
Yeah.
I can put it back on the... So we're putting stuff basically in front of the CPU. Like, here is the data, please work with it. So we are aligning up the data, like from 100, put into X1. We're basically creating this, we're preparing where the holes are going to be punched. Because then you do hole punch.
Yeah!
And I'll show you an actual example in a bit, but you would then, since you lined up the data, you said like, oh, in the first one goes from 100, and then in the second one goes 1, etc., etc. And then you say 1 and 2 are added together, 3 and 4 are added together, and then you can say store into 100 what was in X0, because that's where the result is going to be. So you can see that I lined up the data, I did the hole punch, and then...
So when something's stored though, so we've hole punched our paper,
Yeah.
and we're putting the paper back in the binder.
Yeah.
Is that an action happening on the computer?
Yeah.
So the lining it all up,
Mhm.
hole punching is kind of deciding what the action is.
Yeah.
And then storing it is like, now the zombie has moved a little bit.
Yeah. So if we think of this as 3 actions, first of all is just lining up the data.
Yeah.
Where's it going to be? What's the data? Getting it all there in front of the CPU. Then we perform the add action, or we can think of it as...
So now it's being told this is what's going to happen with the zombie.
Yeah, or this is what's gonna... It doesn't even know it's a zombie.
Yeah.
It's just numbers.
This is what's going to happen to this other number set.
Yeah. So here's a bunch of numbers,
Yeah.
add them together.
Yeah.
And now, since they're added together, the result is in the first number that's added together. So if you add X0 and X1, the result is in X0. That's how that functions. So this is an actual example. And when you are writing code, you're normally not writing it like this. You're writing it in a higher level language like C++. And a lot of the compilers for C++, what they will do is they will detect that you are doing this kind of behavior. You are basically lining up a bunch of numbers, and they say, aha, I know how to optimize this by basically reducing it down to a couple of loads, a hole punch, and then a store. And I can actually show you an example. So here we have some C++. We have a struct called zombie. A struct is just a class. It holds values together. Here it's holding an X and a Y position. Then ... we have some code. Somewhere later, we are incrementing the X and the Y value from some sort of movement value. So a zombie needs to move X and needs to move Y. So the X and the Y in the array of zombies needs to be incremented by that.
And that's the 0 and the 1 there.
Yeah. So the first element in the zombie array give me the X value incremented by movement X. The first value in the zombie array, the Y value incremented by zombie Y, etc., etc. The compiler will see this and say, aha, instead of going to this kind of code, there we go, this, which is correct.
It just takes longer.
It takes longer because you can't do many things at once. So if you want to have 1 million zombies, this doesn't work. So if we go back, it will look at this and say, I could do it that way, sure, but
I know better.
I've looked at everything around you and I see we can actually turn this into something smarter. So I'm going to show you actual assembly output. You don't have to know what's going on, but I love it
when I have no idea what's going on.
Same. But I just wanted to show you that this is actually happening.
Okay.
And it's very different based on, because the compiler has hundreds of ways to optimize. This is just one of them. So we have here our actual assembly instructions, but it's again these 3 things. So the first part after #load, that's the loading into these XMM registers. It does some stuff above to get the numbers, but it's unpacking and moving data around, which is basically put them in the right registers in the right place. And then you see we have add PS, which is just saying add those numbers together. It's hole punch.
Oh, yeah, that's PS there. Yeah.
Yeah. So it's a hole punch. Add PS from XMM4, XMM1, XMM0. That's it. And then it also found a way to store all the data in one action, the move UPS.
So suddenly we've turned a bunch of zombies moving into one action that's all being added together.
Yeah.
Into one thing that's being stored.
Yeah.
So like technically, say if you have a field full of zombies and they all need to move a little bit, that would just look like this.
It would look, so if the compiler is able to see that, hey, I'm going to be adding together 1,000 zombies or 100 zombies or whatever that is, and I know what the data is, it can line them up into one of these or maybe multiple of these. We pay a little bit for the load, and I can we talk about later in the RAM episode where we can actually avoid some of that load, or we don't feel the impact of the load as much as before. And then summing up all the numbers, basically changing all the values, is 2 instructions. And these are some of the specialized systems within a CPU. Like normally a CPU, because we talked about in the first episode, like, oh, we have this arithmetic unit. We can add 2 numbers together. But CPUs have gone way beyond that. I even tried for this episode to create an example of, like, here is the unoptimized version. Here is some assembly that looks like stuff that we are familiar with. But the compiler was so adamant on optimizing the code that it was basically impossible for me to get plain old assembly out.
It's too smart.
It was also like, no, let me take care of this.
Machines are taking over. We're all gonna die.
Like I was like taking up zombies, putting in some numbers, and then the compiler was like, oh, you're never actually using these values. So it basically deleted all of my code because it saw like, oh, he's adding numbers, he's putting stuff together.
This is a bunch of wasted space. Why you do this?
And then he's never using it. So it's like, oh, because I'm trying to write some example code, and then he just threw it away. So it's like, oh, okay, no, don't. I'm actually going to be using this.
My
it's fine.
work.
And then it was like, oh, you're doing +1 on all these things. Let me do some cool tricks that will actually speed up. But then it looked really bad for the example. So I was trying my best to like create an example, but the compiler was always like, no, I know what you're doing.
I see through you.
It really didn't want the classic load add because it's like, no, that's slow. Even though like relatively it's pretty fast, but it was like, no, you don't want that in your actual code.
I know what you want.
Yeah, you want hole punch.
Yeah, hole punch. One easy action.
One easy action. So yeah.
Cool. So basically, between the CPU and the RAM, what's the main actions that are happening?
So when the CPU wants some data, it would retrieve them. Like here we're doing a move or an unpack, or you can actually just fetch data from RAM. It's giving the CPU, or the CPU is giving the system or the control unit a memory address.
Okay.
And it would say, hey,
this information is stored in this memory address. Go there to get it.
Yeah, go to this memory address and give me whatever's there, because it's always going to be a number. But then it fetches it and puts it in some register, but it also goes into the caches along the way.
Is the CPU reading what it needs to do from the register? That's where it's being told, move everything one step.
Yes, that's the part of the decode step.
Okay.
So when it's reading these instructions, it's saying like, okay, there's an instruction here. What is the instruction? Let's decode the instruction. And then it figured out, oh, it's a load instruction. Let's talk to some control unit or some way of loading memory. Let's load that memory in. And that's exactly from like last episode when we did the pipelining of you want to layer these things just so the CPU can do stuff while it's waiting for data. Yeah.
Cool. CPUs are complicated. RAM is complicated.
It's very complicated.
But this is a good segue into what's the future, because we're going to be talking about RAM now.
We're going to talk about RAM next time. Might not go as low level as we did with the CPU, but at least we'll look at some fun stuff.
Giving people a good idea of how RAM works to also help your CPU, to help everything in your computer, to create some cool experiences.
Yes, sir.
Sweet.
Sweet.
Well, see you next time.
Bye.
Bye.